I think we can go ahead and get started. So yeah, it's my pleasure to introduce today's seminar speaker, Ben Farr. Ben Farr is an associate professor at the University of Oregon and an expert on things related to gravitational waves, especially the sources detected by LIGO, Virgo, and Cagra. And Ben has actually held like a whole bunch of leadership positions within the collaboration. Also, he's currently leading the O4A, the first part of O4 paper on the astrophysical interpretations of our binary black hole mergers together with Aditya here. But he's not going to tell you about that because it's still a secret. And yeah, but there's a lot of super interesting work that he and his group have done on all the data that we do have published, and I'll just let Ben tell you about that now.
All right, great. Thanks for having me. It's a pleasure to be here. I've been in the area for a lot of my academic career and across the lake and Rochester for undergrad, for example. Been to Toronto a bunch of times for my first time to see it, so I'm really happy to be here. Tell you a little bit about the work that my group has been doing. Good, so let's get into it. First, slides are available here if you feel like following along. I always like to put the link to the slides in here for folks that can't see the screen or whatever. You can always go back and take a look at the slides. But first, I'll very briefly cover my group and a bunch of the projects that we're working on. I'll be around for the rest of today and all of tomorrow, so let me know if anything strikes your fancy. I'd love to chat about any of the stuff, even the stuff that I don't go into depth on today. The graduate students in my group, JD Merritt, Sangeet Paul, Jackson Godfrey, Yvonne Juarez Reyes, and Claire Nell, have a smattering from senior to junior, along with a couple of undergraduates that have been getting involved with various projects in the group. Some of the stuff that we've been doing that I won't get a chance to go into detail on today. One is in modeling the noise of LIGO, so not the well-behaved Gaussian stationary background, but the noise transients that can often look a lot like the astrophysical transients that we are going after. JD has led the development of a principal component analysis-based project that we've led in trying to build parameterized models for these noise transients. That gives us the ability to do lots of things, one of them being to simulate additional noise transients. We can also go at them with our parameterized models and marginalize over the presence of them in conjunction with astrophysical models, along with lots of other things. There's a lot of powerful things that we can do if we have useful parameterized models of noise transients, and so that's a project that he's been working on. Sangeet has been working instead on the usually well-behaved Gaussian stationary background and building parameterized power spectral density models that we can use when we characterize individual compact binaries in order to marginalize over differences, changes in behavior to that background noise and uncertainty in our ability to characterize it. And so this is work that he's been doing for quite a while. We're implementing it in the PE tools that LIGO uses to characterize our astrophysical transients. Another project that Sangeet has done is build up a Python-based library that has a whole bunch of tools for doing Bayesian clustering. So clustering is something we don't typically think of in Bayesian context, but there are many Bayesian approaches to conducting clustering and being able to marginalize over uncertainty and classification of events in clusters. And so it's been building up a really nice tool to do that. And Sangeet has also been working on a phenomenological model for black holes that exist in dynamical environments. So using this mathematical framework of coagulation and being able to kind of have simplified but powerful descriptions of black holes that can interact and have hierarchical mergers. And so he's most recently been looking at applying this to predictions from the AGN channel. And finally, JD has also been working on a project in population synthesis world. So in working with the Compass library and modernizing the treatment of winds in that code. So I'll talk a little bit about population synthesis today, but the basic of it is that you are taking a simplified description of stellar populations and trying to make predictions for the transient catalog that we detect with LIGO, Virgo, Cagra. The Compass model is one of the many out there in PopSynth world, and JD's been doing a huge effort in updating all of the different wind models that are available inside of that package. All right, so now on to what I will talk about today, and that is going to be focusing especially on data-driven models for understanding our catalog. And so first, just a case study in data-driven modeling in a Bayesian context. I am going to show you a time series here. So this is not a gravitational wave strain. Instead, this is a simulated light curve of what some extraterrestrial species would see if they looked at the reflected light from Earth. And so this is the intensity of light reflected from Earth as a function of time. And you can see the obvious imprint here of days. And the question is, what can you learn from this time series? And especially, how can we use a data-driven model to try to do the best we can? So here is a full year of data, and I'm zooming on 5 epochs here. So this is the data that's going to go into the fit that I'm about to show. So just these 5 different 24-hour periods and looking at the change in reflected light over those 24 hours. Now, using a data-driven model, we're going to try to model what the reflected light across the surface of Earth looks like. So in other words, we are building up an albedo map, a pixelated albedo map of Earth, and informing it just from these 5 days of reflected light. And so this is the library that we wrote to do it, Exocartographer. You can go to the slides and grab the link if you're interested in what the code is doing. But this is the inference that we get. So again, each pixel here is showing you a free parameter in the model, and the brightness is giving you our inferred albedo of that pixel. And so if you squint, or if you're in the back of the room, you don't need to squint, maybe it will start to look a little familiar. And so to give you a reference here, it's a little hard to see the light. Here's the map that we use to simulate that data set. Thank you. Go back there. All right, so there you go. So if we go back and forth, you can see some of those brightest features here. So one of the most dominant features of the Sahara Desert here in northern Africa, that pops out really brightly just from those 4 days or 5 days of reflected light observations that we had. Another feature here is the darkness of the Pacific Ocean. And so I think this is a really nice illustration of what some data-driven models can do in the context of, in this case, time series information. And so specifically, question back.
So just to clarify, that really is from one impact parameter.
From one
impact parameter. You're simulating, or maybe this is actual data.
So this is simulated data,
yeah.
And this is the simulated data right here.
You're assuming that the observer is just at some impact parameter.
Right.
Or you're in principle folding in data from different orientations.
Yeah, thank you. So no, we're not folding in different orientations. We are fitting for the orbital parameters and the viewing angle. So I cheated in making this data set, and I put Earth's obliquity at 90 degrees. The reason being that if we didn't have access to all of the latitudes of the map, then there'd be infinite uncertainty in parts of this map, which isn't very fun to show. But yeah, so this is using one specific obliquity, one specific viewing angle.
Can you give us a qualitative sense for how much the map might be fuzzed out if it was at 22 degrees?
22 degrees, yeah.
Whatever it is.
Yeah, so you'd expect basically the latitudes that you'd never see, you just don't get any information on. And the other thing I'm not showing here is there is quantified uncertainty on the albedo of each one of these pixels. That would be a companion map or something if I showed it to show you what the uncertainty is on this albedo map. But yeah, so and specifically what the model is here is each one of these, the albedo of each one of these pixels is a free parameter, and then we have a Gaussian process prior that is putting in the regularization, that is preferring some amount of smoothness on this map to fill in the gaps. All right, good. So now on to gravitational waves, and I'll start off talking about our observatories. Now, I know a lot of people in the room have heard a lot about gravitational waves, but I also was told that there might be some students in the room, so I'm going to cover from the basics really briefly, and don't hesitate to interrupt me if I skip over something or I go past through something that you have a question about. So here is our network. I think everybody knows our network. We have the 2 LIGO detectors that are operating in the current observing run, O4A or O4B right now, along with Virgo. Kagra has been doing lots of excellent work on commissioning, but has yet to reach astrophysical sensitivity, but is chugging along, and LIGO India is a construction project underway. So here's a picture of our sensitivity. In blue is LIGO Hanford, red LIGO Livingston, and green Virgo. And the one thing that I will highlight here beyond just our usual bucket with peak sensitivity somewhere around 100 Hertz is the strain sensitivity of 10 to the minus 23. And now I know that this is something that you have probably been told before, but I'm going to say it again because I think it's really cool. This is an incredibly, incredibly precise measurement, the most precise measurement I think humans have ever made. So to put this into context, 10 to the minus 23, so 1 part in 10 to the 23. I usually like to use, when I'm teaching my intro astronomy course, I like these grains of sand to talk about the numbers of stars, but there's only 10 to the 18 or so grains of sand on Earth, and that's nowhere near 10 to the 23 that we're talking about here. So instead, I'll talk about cells in the human body. Crowd participation here. Anyone want to guess order of magnitude how many cells are in the human body? What's that? 10 to the 12? All right, good, yeah, 10 to the 12, 10 to the 13. I think that's probably within the uncertainty of our ability to count up cells in the human body. So from what I've Googled in the biology circles, there's somewhere around 10 to the 12, 10 to the 13 cells in the human body. And so we're not even close, but if we take the global population of around 10 billion, that gets us there. So measurements of strain with LIGO is equivalent to telling there is one missing cell from the entire human population, which is pretty nuts. But why do we need to make such precise measurements? Why is strain so tiny? One way of looking at this that I like from Ray Weiss is coming up with the Young's modulus for spacetime. So this is a really just simple classical argument doing dimensional analysis. What would you derive from fundamental constants for the Young's modulus of spacetime? So relating strain to force. And so we take our C's and our G's and some F's along the way to make something that has the right units. We plug in our peak sensitivity of around 100 hertz for the frequency, and you get something like 10 to the 27 pascals times that 100 hertz squared, or about 10 to the 20 times that of steel. So in other words, space-time is incredibly, incredibly stiff, and it takes extreme distortions of it, a lot of energy dumped in to make even the tiny strains that LIGO is trying to detect. All right, so I've got this forest and tree analogy, and the first thing I will talk about are our trees, our compact binary mergers. So you have all probably seen animations like this before. Go back and play here. So this is a numerical relativity simulation of a GW150914-like binary in its final phases of merger. And so we are sensitive to this waveform down here in our various instruments, and we're in the in-spiral phase right here where we have this slow progression from low amplitude to high amplitude and low frequency to high frequency as the two black holes approach one another. And then we hit the point where they plunge into one another. You have an event horizon that's shared between the two, and we get this settling ring down of the final steady state black hole. And so that is the thing we are after. This is what the waveform looks like if we were infinitely sensitive. And as you surely know, we are not infinitely sensitive. We have noise in our detectors. And so this is more what that signal looks like. So this is showing the whitened data from LIGO, Hanford, and Livingston for GW150914. By whitened here, what we do is we take our strain data, we FFT it, we go to the frequency domain, we divide by that amplitude spectral density that I was showing you to show you the sensitivity of the various detectors, and then we go back to the time domain to get this strain here where now we have equal contributions from all frequencies that we are looking at for the data. On top of that, we have our recovery of the signal using both principled GR assuming waveform models as well as data-driven models, but this time in time frequency space where we think of like using sine Gaussian wavelets to build up a pixelated picture of what the signal looks like in a spectrogram. And they are very consistent and also uncertain. So there's uncertainty in the measurement of the signal, which translates to uncertainty in the measurement of the properties of each one of these events in the catalog, and there's also additional uncertainty on the astrophysical parameters, which is degeneracies in our model. All of that turning into uncertainty in our measurement of individual parts of individual characteristics of this binary. So for this, we're using Bayesian analysis. Once again, the goal here to characterize our source is to estimate the posterior probability density function. This data here folds in all of the parameters that define our binary. So in the case of a circularized processing compact binary or binary black hole system, we would have 15 free parameters to fit. And so this is the kind of thing that we get when characterizing a single compact binary. So I don't mean for you to read these axis labels, but there are masses and spins. So 6 degrees of freedom on the spins. There's distance to the binary, sky location, orientation of the binary, et cetera, that build up to those 15 free parameters. And the posterior is non-trivial across those 15 dimensions. And so we really want to fold in all of the information that the data has to offer from each one of these events in a principled way to infer details about the population that is building up our gravitational wave transient All right, so with that, we will get to our forest. And so this gravitational wave transient catalog is the biggest data product currently coming out of the LIGO-Virgo-Kagra collaboration. We are now beyond our third gravitational wave transient catalog, the first one being over here. So each one of these figures is showing you the 90% credible interval in mass space of all of the events in that being updated in that catalog. So over here in GWTC1, we've got a handful of binary black hole systems going down here to low masses. And so I'll just point out these characteristic shapes up here at high masses. So this is 80 solar masses, 60 solar masses, 40 solar masses. In terms of primary mass, we go from these shapes of elongated ellipses here at high mass, where we're effectively sensitive to total mass, going down here to 20 solar masses or so. We get those banana shapes, and that's where we're really constraining the chirp mass, this characteristic combination of masses that we're sensitive to from the in-spiral phase of the waveform predominantly. So going up to further catalogs, we add more and more and more events. And the idea is now, how do we extract as much information as we can from these catalogs? This is giving you a picture of how that catalog is growing. So down here, we've got observing time in days, getting up to, let's see, over 1,000 days of total observing time now since the start of 01, which is pretty crazy. And then here we're showing the cumulative number of events going into that catalog. And so the slope here is giving you a sense of the sensitivity of our detectors. Every time we hit a new observing run after doing a long break spent on commissioning and improving the sensitivity of the detectors, that slope increases a little bit, showing that that work wasn't for nothing. And so you can see we're going up pretty steeply now. We're at over 200 events that we've released publicly on our online database. So far, we have published papers leading up through the end of 03. We are currently at work on 04A, and we are currently building up the catalog for 04. All right, and so again, slope gives you sensitivity. Where my eye goes every single time I show this is down at the very end of 02. In August of 2017, Poisson statistics were fortunate. In that month of August 2017, we had a lot of events there. That's when 17.17 happened, obviously. And it bothers me that the slope is about the same as 03. It makes you think that we actually made some commissioning improvements to the sensitivity that got us the same kind of sensitivity we saw in 03, which is not the case. It just was a random fluctuation of Poisson statistics, but still a little weird to look at in this figure nonetheless. All right, good. So now let's talk about how we go about constraining our populations from these catalogs. So in that previous form of Bayes' theorem that I showed you, we had this prior distribution. So this is meant to encapsulate our prior information on the individual properties of binaries going into the catalog. And so we use uninformative priors for this. Think uniform in mass, uniform in local volume, etc. But ideally, this is the thing that we're actually after inferring, which should be the astrophysical distribution that these systems are being drawn from. And so what we do now is replace that prior with something that's parameterized, and now we have some more parameters along for the ride that are now describing not the properties of individual binaries, but properties of the entire population. So let's say you want to fit a power law distribution to the mass, your power law index is going to be folded into this big lambda. All right, so now we have Bayes' theorem, and we had our single event coseers that I was showing here before, where our analysis is effectively replacing those fiducial priors now with parameterized ones, and we want to fit the hyperparameters that go into that population. So, pointer to a paper for some people here in the crowd. This is a diagrammatic way to look at our population model. So a directed acyclical graph can give you a very convenient way to visualize one of our hierarchical models. And so this is describing the data generation process that goes into making our transient catalogs. So over here, we'll think about this as like a forward way to model the data. And remember, our lambda here are the hyperparameters that characterize our population. So once you pin down the astrophysical population, you draw from that some number of sources that we are going to observe. So those are the thetas here are the true source parameters for each of the events that are going to go into our catalog. Once you have your true parameters, you can take our prediction, our models of GR, and our understanding of the noise and generate data. And then once you have the data, you can figure out whether or not that would have been detected. So if that has a detection statistic that passes our threshold. All right. And so this is generating the whole catalog. And this plate here is saying that each one of our observations are independent statistically of the others. So in other words, the noise that goes into making our data, for example, is independent across different events in our catalog. And this is representing the fact that we detected those events. All right, so then putting this all together into a likelihood, we have the same likelihood that you would construct if you wanted to characterize the splotches of gum on patches of sidewalk or numbers of stars in some section of the sky. It's an inhomogeneous Poisson point process. So we take the Poisson process, which we often think about in a time domain, but apply it spatially, right? And so not only is it a Poisson process spatially, it's one that has a rate that changes as a function of the parameters that we are looking at. So in this case, masses and spins of compact binaries. All right, and so we can put this all together to write down our population level posterior distribution, and I'm writing it here over both the hyperparameters and the details of all of the sources, which remember are uncertain. And so we've got a bunch of different components here. There's a prior on now our hyperparameters. There's this term here that's quantifying our sensitivity. So this term is basically an estimate of the fraction of our guessed population that we would have expected to detect. Based and then risen to this power of our number of observed binaries in the catalog. And then over here, we have the contribution of information from each event in the catalog. And this is just our normal strain likelihood, if we were to go all the way back to the data, as well as now our population model that's describing the source parameters based on our guess at all the hyperparameters. So this is the thing that we want to infer from our catalog. All right, and then what are we getting after here? So there's lots of different physics that we don't understand that goes into making the gravitational wave transient catalog. Just a quick illustration of some of the many proposed channels that we could produce compact binaries using, globally separating them based on here isolated evolution. So think not in dense stellar environments where you expect a lot of dynamical interaction, but stars that are born gravitationally bound together. Dynamical assembly being in dense star clusters, so think AGN, globular clusters, etc. And then gas assisted, so we need to invoke things to make the binaries tight enough that gravitational radiation can lead to their merger in less than a Hubble time. And so classically speaking, we've long thought about things in the isolated channel, especially stable mass transfer and common envelope being really typical methods to make the binaries tight. So they start off wide, such that normal stellar evolution doesn't lead to stellar merger before you form your compact objects. And then using common envelope phases, for example, to then have dynamical friction, bring them close enough that gravitational radiation can take over. And then globular clusters have long been looked at as potential sources, and there's been a lot of work on AGN, especially lately. So lots of unknown physics that we hope to start constraining with our catalog. And why not just use some of these models that we're simulating sources from to just fit to the catalog directly? And that answer is probably obvious. There's way too much unknown physics in these models to be able to fit them to the catalog directly. They're also, depending on the model, often very computationally expensive and not usable in the long kind of MCMCs that we often have to use to fit the posterior distribution of the full hierarchical likelihood. So here's COMPASS for an example. I've talked about COMPASS a little bit already. This is one of the many population synthesis codes out there. This is just a quick look at a bunch of things that are fixed in the code, not even things that are often fit. In this constants.h file, which is over 6,000 lines. So there's a lot of stuff here for common envelope prescriptions, for example, just to highlight a few. And so there's lots of unknown physics here. Using this to fit the data directly is a very tricky problem. You can take bite-sized pieces and focus on individual things, but then you have to worry about correlations with the things that you're fixing when you do that. And so for now, we're going to look at using some either parameterized models or phenomenological models that fit the catalog, try to learn features from it, and then fit those to predictions from simulations. So just an illustration from back with 150914 of two possible ways to get to a binary that looked like 150914. So here's an isolated evolution scenario where we have a common envelope phase that brings them together. And then here's a picture in a globular cluster where we have loads and loads and loads of different interactions and scattering events that would lead to making something like 150914. All right, and then here is a picture of the global landscape. And again, you're not meant to be able to read anything from here, but this is providing you just a picture of the uncertainty on the overall rates. So not saying anything about the shapes of the distributions, just the total number of mergers we would expect for binary neutron stars neutron star black hole systems and binary black hole systems. And this is bringing together predictions from loads of different channels within the literature. So from short gamma ray bursts, kilinovae, triples, multiples over here on the binary neutron star side, chemically homogeneous evolution, young and open clusters, globular clusters, and then over here for BVHs, those same models along with population 3 stars, etc. So this is just to show you that there's a huge amount of uncertainty on the theory side, just when it comes to rates, not even talking about the shapes. So there's a lot of uncertainty on the theoretical side that we need to help to constrain. And so how do we do that with the catalog? What we did first was, the first thing you do when you have 2, maybe 3 points, you fit them with a line on the log-log plot. So the very first thing we did before GWTC1, actually, this was a paper that we called the 01 BVH paper. It was before we got ourselves together and actually started naming our catalogs in a sensible way. This was the first population fit that we did on the catalog, and it was fitting a power law distribution of the mass and constraining the index of that power law. So looking forward to 02 with our first gravitational wave transient catalog, we were able to start fitting some additional features in the data. So we did have a power law model that we fit, and we were able to put in a truncation and start to look for evidence of there being a lower and upper mass for black hole systems, and then possibly a bump. So this was the first time that we tried to model some excess of events somewhere that deviates from the power law behavior, though at the time the data wasn't conclusive in there being a bump in the data for that first transient catalog. And then moving on to GWTC2, this was a paper led by Maya. We started to use a few different parameterized models here. So we had, again, this truncated power law distribution. We also looked at a broken power law, a power law with this Gaussian peak, which has survived all the way up through 03, actually. And then a potential multi-peak model here where we put in a second potential bump in the mass distribution. We also, so here is showing you constraints on spin magnitude and misalignment. So this is cosine of the tilt, where 1 here would mean a binary system where the spins are aligned with the orbital angular momentum, and then -1 over here would be anti-aligned. And then finally down here, looking at the merger rate as a function of redshift, and the dashed line here is showing for comparison the evolution with star formation. So we're seeing here for the first time evidence that the catalog looks to be evolving with the star formation rate and redshift. All right. Good. All right, we're cooking some stuff. All right. So now on to what my group really focuses on. So these are often called non-parametric models. They are sometimes semi-parametric, and depending on how they're applied, I think they're very parametric. There are a ton of free parameters in these models in practice that we are fitting to the data. So calling them non-parametric is I think, not doing them justice. And so I like to focus on just calling them data-driven. The idea here is that we put in a lot of flexibility in the model so that we don't need to guess at what features are in the data before we go to fit. So what we're looking for here is being able to come up with a modeling approach that's going to scale with the catalog as it continues to grow. So we're already beyond 200 events in the catalog. We have been able to find features in the mass distribution going from truncations to 1 peak, possibly 2, to breaks in potential power laws. And the idea here is, one, we want to make sure we're not missing anything, that nothing is getting left on the cutting room floor just because we didn't think about a parameterized distribution that could fit it. And the other is being able to extend this now to very big catalogs as we look to end of 04 to 05 and beyond. And so the data-driven model that my group focuses on are splines. And so here is a picture of parameterized cubic splines. So the way to think about this, splines are just a convenient way to interpolate between points, and these points that we are interpolating between, these knots, are the things that you can think of as being the free parameters. So now our population model is not a power law index. The free parameter in our population model is not a power law index, but the location of these spline points, these control knots, and they're the things that we want to infer from the data and then look at the interpolated distribution to look at what the overall astrophysical distribution is looking like. So now looking at this being applied in a regression context, so let's throw down a bunch of data here and use this parameterized spline model to fit the underlying function here that is generating this data. So now we have these control points again. These are going to be the things that are free parameters in our model. Down here are the residuals. This is ultimately what's going into the likelihood and should be Gaussian if we are doing a good job at fitting the underlying function. And then we turn the crank on our MCMC, fitting a bunch of different values for all of these spline control points and generating a posterior distribution over them. All right, so that's the picture of using these data-driven models in this Bayesian analysis framework. And then when we apply it to our transient catalog, so cutoff over here, this is looking at the distribution in primary mass. So here's primary mass, and this is going to be the differential rate in primary mass. Here's one draw from our population model. Here's another draw that's consistent with the data. We again turn the crank on our MCMC a few thousand steps, and we get this spaghetti mess of different guesses as at the mass distribution of the black holes from the catalog. And then we draw credible intervals around this, and these are the regions that we show in our paper. So this is giving you what the overall distribution looks like based on our data-driven fits to the catalog. And so we can see here, we've got a peak here at 35 solar masses. We've got a sharp peak here at 10 solar masses. And this, even though this was the first peak that popped out chronologically as we've been building up our catalog, this is really the dominant feature in the catalog now. This 10 solar mass peak, we're seeing lots of events in this 10 solar mass peak. It was suppressed in earlier catalogs because of our sensitivity. We are more sensitive to high mass binary black hole mergers than we are to low mass ones. And so there's less volume times time that we observe here compared to here. But now that we have collected a decent amount of observing time, we see lots of events in this peak. It seems to be very sharp at 10 solar masses. And then potentially this 25 solar mass peak here, though this is the most nebulous of the features. And so depending on choices of prior, this can kind of get washed out or not, depending on your approach to fitting the data. All right, and so we've taken a couple of different approaches to how we apply these splines in practice. So our first approach was actually to use them in conjunction with some of the parameterized models we had been using up until this point. So for example, you can think of fitting the mass distribution not with a spline off the bat, but let's say you fit it as a power law, but you take that power law and you allow it to be modulated by some data-driven model like a spline. That has some nice features in it. If there's a reason, a physical motivation for why you might fit a power law to your distribution, for example, then you have a nicely nested model where your default assumption of a power law behavior is the most likely a priori, and then you allow for deviations from that based on what the data demand. And so that was our first use of splines. Since then, and actually using that technique, we found the 35 solar mass peak, but we were also one of the first to find the evidence of this 10 solar mass peak in the earlier catalogs. So now looking to what we can do in GWTC3, this is from our GWTC3 populations paper, and showing you the constraints across a couple of different data-driven models. So the power law spline is PS in here. That's the yellow one giving you the 25 solar mass peak and the 35. This purple one is actually motivated by the first data-driven model that I kicked off the talk with, talking about the albedo map. This is the same kind of approach applied to the gravitational wave transient catalog, where you fit the population with this kind of bin histogram, and the heights of the bins are your free parameters, and then there's a Gaussian process prior distribution that regulates the smoothness of that histogram. So that's shown here in purple, and then there's a couple of others. There's a Gaussian mixture model in here as well, and all of them seem to find the same general features. There's a 10 solar mass peak, there's a 35 solar mass peak, and then differing amounts of certainty on the presence of that third peak here at 25 solar masses.
So the horizontal axis is total mass?
Primary mass, sorry.
Primary.
Yes, yeah. Primary mass here, and then the differential rate on the y-axis. Yeah, thank you. All right, so good. And so we focused first on the mass distribution, as did most of the data-driven models. But then we wanted to extend that to all of the other dimensions. So other dimensions are not quite as informed as our mass distribution, but we have the same motivation for looking at them with flexible models as we do the mass distribution. So again, mass distribution down here, this is the look at the mass ratio. Over here is the spin magnitude. So you can see that we recover preferentially low spin for the black holes in the catalog. This peak here is around 0.2. The fact that it doesn't necessarily peak at 0 spin is actually a combination of things, but can be tied to our likelihood. And so I'll talk a little bit about the limitations of our likelihood estimation and ways that we can fix that tomorrow in our gravitational wave repeating for those that are going to come. And then over here is our spin distribution. So On the right, if it were peaking here, that would be preferential alignment with the orbit. And then uniform distribution here would indicate isotropically oriented spins. And so, for example, we'd expect isotropically distributed spins if a dynamical formation were the dominant one. And we expect something probably peaking at cosine tilde of 1 for a field formation channel where there's various physical mechanisms we expect might align the spins with the orbit. And then finally up here is our fit to the rate versus redshift. So the smooth band here is showing the power law fit that we did in the catalog. And then the blue wiggly thing here is showing the constraints of the spline. And so while there's not clear evidence of deviation from a power law here, the uncertainty here is pretty appreciable. There is some suggestion of there being interesting development, interesting features with the redshift. So we're looking to this with excited eyes in future catalogs as we get more data. All right, and so now this is fitting each dimension individually with a one-dimensional spline and not able to model potential correlations. And so the question is, what can we do to extend these data-driven models to look for correlations between parameters, say between mass and spin? And so this is one work led by my student Jackson. She did a ton of work in putting together these spline models. The first, so there are obviously higher dimensional splines. There are bivariate splines, et cetera, that you can construct in similar ways. I think that our likelihood is limiting it, and part of the motivation for the stuff I'll talk about tomorrow. But we can also take these one-dimensional splines and use them creatively in mixture models to try to isolate individual features in one dimension and look at their properties in other dimensions. And so that was the motivation behind Jackson's paper here. And so what we did was we took our mass distribution and we fit it with our flexible model, but additively with a Gaussian that is able to describe one of the peaks. And so this is a spline plus a peak with an unknown mixing fraction that we fit for. And what we do is we associate a different spin distribution with the events that are put into the peak versus the ones that are in the spline continuum. And we look for evidence of there being a difference in the spin population of the events in the 10 solar mass peak with the events across the rest of the mass spectrum. And so down here is showing our constraints on spin magnitude over here and on tilt over here. In red is showing the spin distribution we infer from the events in the peak, and in green is showing the rest of them. And so what we find is that the 10 solar mass peak is even more preferentially low spin than we get from looking at just the rest of the catalog altogether. And likewise, the tilt, the spin distribution, the orientation of the spins is preferentially aligned, more so than when we look at the catalog as a whole. And so all of this is pointing toward consistency with the 10 solar mass peak and an isolated formation channel. So what we expect from an isolated formation channel is probably low spin, though it depends on who you talk to, but definitely preferential alignment. And those are the two things that we see really standing out when we focus on the 10 solar mass peak alone. All right, and so with what time I have left, I want to talk about what comes next. But first I want to pause here. That's going to be the extent of talking about our population fits to the catalogs that we have so far. All right, I'll leave some time again for discussion too. Okay, all right, so what comes next? Right now, LIGO has funding to get us through the end of the 5th observing run. We're currently in 04. We have plans for upgrades that are going to happen in between 04 and 05, and then we have plans to run 05 for a couple of years. But that won't be, we don't expect that to be the end of life for the current LIGO facilities, and it certainly won't see us to what we expect the next generation timeline of detectors to be. And so I was on the study team that was charged with proposing what we can do with current detector facilities to bridge that gap between current generation detectors and next generation detectors. And I was specifically put in charge of the science case and what kind of science we can do with the types of technology that we can see implementing on these types of timescales. And so this is giving you a picture of what we think is possible. So the boldest line here in yellow is something we call A sharp, and that is a configuration that we think is attainable with current technology using a few key upgrades, one of them being the coatings that we use on the mirrors, moving to a crystalline type coating. And for comparison, this is the 03 LIGO Livingston sensitivity. And in light blue here is what we think the design A+, so what we hope to achieve in 05 will be. And so we think we can get down at least a factor 2 more sensitive between O5 and what we'll hopefully see as the next generation of observatories being built. And so for sensitivity, now on the x-axis here is total mass. Here is 100 solar masses. And on the y-axis is the horizon redshift we can reach with these different designs. A sharp here is, again, in yellow. And so redshift of several we think we can reach here in the peak of our sensitivity at a little under 100 solar masses. All right, so that would get us probably thousands of BBHs a year. And so, question, yeah?
Yeah, I get what you anticipating your next slide. What do you gain by going to higher redshifts, like beyond the order 2 that you might get?
Right, so here we're looking beyond the peak of star formation, right? So we start to get diminishing returns as we push those. Yeah, so not so much in the BBH world, but what down here, I guess, where you can look at is the binary neutron star right here. So there we're not even getting out to redshift 2 yet for BNSs, right? So I think the real payoff there in terms of expecting the numbers to scale like we would hope is focusing on the low mass end. But here on the high mass end, we're certainly pushing past the peak of star formation and being able to look at maybe reaching interesting redshifts for population 3, I don't know. But I think the compelling case is that we're going to definitely push into detecting most BBH mergers and hopefully a good fraction of the BNS mergers. All right, good. And so now next generation. So in the US, our hope for the next generation of detector is called Cosmic Explorer. This is really just LIGO on steroids to a large extent. Take our 4-kilometer design and scale it up to 40 kilometers and hopefully build 2 of them. Being a little bit compromising, maybe we build 140 and 120 kilometer detector, but overall, the general features are still the same. We still have room temperature, optics going on, we use squeezing, we do all of the same stuff that we do with LIGO, but now scaling it up to 40 kilometers. In Europe, the concept is Einstein telescope. This is using a bunch of new technologies, so this will involve going underground like the COGRA detectors, it will also involve cryogenics like the COGRA detectors, but able to reach, on paper, at least comparable sensitivity to what we expect to do with Cosmic Explorer. All right, and so what can these things do? This is a picture of where we expect the binary mergers to be happening. So on the left is meant to visualize the binary neutron star mergers. On the right, the binary black hole mergers. And as we move away from the center, we are looking further in redshift. And so the density here is scaling with star formation rate. And these dashed lines are showing the horizons of the various telescopes that observatories we're talking about. And so Cosmic Explorer here is the purple. And so like Reed was just poking at with how far we are looking at BBHs, we are certainly looking past what we think is going to be interesting astrophysically with Cosmic Explorer. So with Cosmic Explorer, we would definitively detect every single binary black hole merger happening in the observable universe, period. We detect every single one of them. And if you look over here on the binary neutron star range, we reach well past the peak of star formation, and we don't detect all of them, but we detect most of the binary neutron star mergers happening in the universe. So what that means is that because our sensitivity to sources scales like the amplitude and not the power. That's really the driver here behind what we could realize as going from detecting the very first gravitational wave to detecting all of the gravitational waves in a single generation, which is pretty insane. And so here is a picture that another Farr and I put out of what Cosmic Explorer data would look like. So this is showing you a simulated spectrogram of 16 minutes or so of Cosmic Explorer data. So x-axis is time, y-axis is frequency. The chirp shapes here are a bunch of mergers happening. And so from left to right, we've got here is a binary black hole merger happening at a redshift of 1.5. Here is, the binary neutron star merger happening, at a redshift of 1. This is a binary black hole merger happening at a redshift of 1.5. Here is a binary neutron star merger happening at a redshift of 2. So no advanced statistical techniques here, just taking a spectrogram and looking at it by eye, and you can pick out these signals is totally nuts. And so what this thing is going to detect is roughly 1 binary black hole merger per 15 minutes. That's how much we think is happening astrophysically. And 1 binary neutron star merger every 10 minutes. And binary neutron star mergers are going to be in the data for an hour. And so what you don't see is piled up down here a whole bunch of binary neutron star mergers that you can't see visually here in the noise at low frequency that all pile up on top of one another. And so with this, the implications for population inference is huge. The resolution that I've been showing you of what we can do with the mass spectrum right now over the entire catalog, we can expect that level of fidelity in measuring the binary black hole mass distribution over every one of 1,000 redshift bins with Cosmic Explorer and Einstein telescope. So the numbers are insane, and what we can do with those we think is really powerful. All right, so with that, I will take any last questions you might have. Thank you.
I had a question about the cosmic presence
Yeah.
stuff that you showed. So when you talk about the 10 solar mass peak, that's like in primary masses, but is it also in a similar range in secondary masses, or like what's the?
Yeah, so what we do is we model the mass ratio as the complementary dimension, and so it does peak at equal masses, and so this does correspond to a similar like peak in secondary mass, but it's not a simple description of what that would look like. We have to go back and calculate that one. Yeah, but actually I should point out, so one thing that Liga had mentioned, had pointed out as being interesting that we didn't really focus on in our original paper was that the mass ratio distribution that we do find for the 10 solar mass peak events doesn't peak actually strongly at equal mass. It peaks more at 0.7 or so, which is consistent with predictions specifically from the stable mass transfer channel, which is interesting. Yeah.
Presumably in your model where you add the gaps to your spline, you use like a mixture model?
Yeah, yes, here.
So then is your spline model normalized inherently?
Is it normal? Yes, so normally this spline distribution is normalized to integrate to 1.
And that's done like when you're fitting for it?
Well, so it depends on the parameterization we use. So here we usually work in log mass, and so we do the normalization numerically. In dimensions where we don't work in log space, then we just normalize it by construction. So we use basis splines and not cubic splines. Right. And so each one of the basis functions is normalized, and the coefficients then just need to sum to 1 to give you a normalized distribution automatically.
I see. Thanks.
Yeah. Yes.
Can you say a bit more about the 10 solar mass peak and what are the issues with interpreting it?
Yeah, so this one's tricky, and like I said, it's a little bit prior and model dependent. It's hard to say what exactly is going on. One thing that I will say, so first of all, is that this peak is very sharp, and the sharpness that I'm showing here is actually limited again by our likelihood. So the way that we compute our likelihood is through importance sampling integrals. And if you make a really sharp feature in your population model and you try to fit that to the data, you run out of effective samples in those importance sampling integrals, and we have to throw away those samples because we don't trust our ability to calculate a likelihood anymore. So this is really driven by what we can do with the data we have. And I think if we had a better ability to compute likelihoods for sharper features, that would get sharper. And so then it's a matter of like, how far do you push some of the events that are maybe in the tail of that peak away from, so really it's like a separate way to ask this is like, what is the consistency of there being a dearth of events at this lower mass end of what might be a peak there? And so I think partly the sharpness of the 10 solar mass peak drives how many events you pile in over here at higher masses. But I think really we just need more data. I think spending too much time focusing on it, especially the GW2C3, I think it's really just a lack of information on the catalog.
Yeah, there was no question asked.
Have I done any glitch veto studies with using chirp transform? Sorry, I'm not sure what chirp transform is. Can I speak up?
It's a fast chirp transform. Where essentially you have the model of Prince and Jenny, where you have cubic terms and other terms coming in in the gravitational wave signal. And then you can actually use the chirp transform where Fresnel integrals come in. And then you can look at the window where you have these signals coming in and track any glitches that come in. I think machine learning may be of relevance here, I think.
Okay, interesting. Yeah, I haven't obviously done anything with the chirp transform. We have started to do some studies of using our models to identify and veto glitches. So from the training example, so what we use gravity SPI classified glitches. So for example, we can come up with a pretty high purity blip glitch training set. We train a parameterized model to give us a parameterized model for blip glitches. And from our fits to that, we also get a population fit of what glitches look like in whatever latent space we've just defined. And so you can use that to make a statistical argument for whether a given transient is consistent with blips or not. So that's something we've been looking at in a search context, but I haven't done anything with the chirp transform.
Very interesting. We have done a little bit of work. I can send that. I'm interested to see if you can follow up on that idea.
Okay, yeah. Let's talk more offline.
Sure, thanks. May I connect with you tomorrow if possible?
Yeah, absolutely. I'll be in the visitor room most of the day.
Thank you very much.
Yeah, thank you.
What's the timeline and the cost of Cosmic Explorer?
So we're looking at 2030s, hopefully. Cost is expensive. So I'm not sure what the current estimates are at. Anyone remember off the top of their head? $1 billion? Yeah, over $1 billion. So
Less than 100 for binary black hole
it's a bargain. So yeah.
But you can say, I won't be back, because there's nothing more to look at.
Right. And so I mean, I think it's hard to see it not sealing the deal with what we could do with ground-based observatories, right? So I think that alone is a very big argument for why it should be funded now. We have the expertise now to build it. We have a plan for keeping LIGO and people around and trained to what we would need as far as timeline for starting to build it. And if we don't do it now, then there's a big loss of sunken cost in developing. We need to build up that expertise in building ground-based detectors again if we want to build it later on. So yeah, and it's expensive. So it's larger. It would be more than the NSF could fund on its own. The NSF being responsible for funding LIGO, obviously. And so we've been worried about trying to spin up other communities and being excited. So we look to maybe the Department of Energy in the US to be able to kick in. They're not super excited yet, but we're still trying to get the high energy community excited for those reasons. One of the dominant costs is excavation. So there's a lot of work going into site selection to try to minimize the amount of excavation we would need. So we're looking for very large empty spaces in the US that are shaped like a bowl so that on a sphere it's roughly flat. We don't need to move a lot of dirt. So there's, and then the other aspect is also indigenous people. So when we're talking about 40-kilometer arms, you're going over a lot of land. We need to build up relationships with all of the potential communities and all of the potential sites that we're looking at. And so there's a lot of feet on the ground effort that needs to happen as well. And that's also very costly, especially early on in the project.
Are spline models prone to finding oscillations that aren't really there, but based off of where nodes are placed?
Yes, yeah, great question. So if I were to tell you that again, we're using B-splines, but let's say we're using cubic splines for the point of easily visualizing it. So if I were to tell you that there's a knot in the spline here, 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 and here, you'd be worried, right? So in practice, though, what we do is we use a huge number of knots, and then we have a prior that is preferring smoothness over those knots. And so in reality, we use like 60 control points evenly spaced on this figure. And then we have a penalty term that is in our prior distribution that penalizes the coefficients of those splines being too different when they're nearby. Yeah, good question.
Another question about this slide.
Yeah.
Is it significant that the spin tilt distribution isn't peaking at a line?
No, so again, here it's also a limitation of our likelihood. So newer analyses that we've done do actually peak harder at tilts of 1.
For both?
For the 10 solar mass peak. The continuum continues to have this exact behavior, which we see across the broader catalog, which is a peak in the tilt distribution, not at 1, which is weird. But yeah, this feature stays roughly looking the same, and if you get a little bit better at calculating the likelihood, this wants to peak a little bit harder at 1.
So that's preferred over, for the continuum one, something that peaks is preferred over something that's flat.
Yeah, so we didn't put in a parameterized model or a non-parameter, like a fixed distribution that's flat. The splines are happy to go flat, and I guess the flat would be maximum a priori, but they like to do this little bit of a peak still. But it gets more pronounced when we separate off the 10 solar mass events that make that distribution have a stronger tail toward 1. Once you separate those, then that distribution tends to get even more weird, like this, peaking away from 1. Yeah.
I guess just following up on this, do you know off the top of your head, actually I don't know this, apologies, off the top of your head what the typical single event posterior uncertainty is for things like masses around 10, primary mass around 10, cosine,
Let me,
I think it's plus or minus 1, it's not plus or minus 10, right?
there's a really good paper figure for this that I don't include because it doesn't show up well on the projector, but we can look at it. This one here. So here is showing the events sorted by their categorization. Here are all the 10 solar mass events. The dashed lines are the single event posterior distributions, and then the blue lines are the reweighed, with the being all lumped together in the peak.
So is it fair to say that the shape of the single event posterior population that forms single event posterior is entirely driven by the underlying population model?
It's driven by which?
Entirely driven by the underlying population model rather than the individual, like you're reweighing.
Yes, yeah, but why they are doing this is look at all of these broader distributions and how well they align given the width of those distributions, right? So
Anyway, I'm meeting with you tomorrow. I'll pick up a nitpicky thing that I have, but I think
okay.
Resolving finer scale things like this, I think, requires incredibly, like exponentially large catalogs.
Okay.
And so it could actually just be we'll talk more about
Okay, cool.
I thank you for bringing this up. I forgot
Yeah.
about this here.
Yeah, good. Cool.
Okay, cool, we're at the hour, so we can continue any more discussion for seniors.
Great, thank you.
I think the sticker price is more than 500 million, less than $1 billion.
Yeah, I remember like $1 billion, I think was.
Well, nothing compared to sending things to space.
Yeah, or building particle colliders.
Yeah.
Very expensive by
Yeah, because you don't need magnets to hold light from Mars.
right.
You just need steel.
You see, and nothingness.
Also, there's
All you need
a
is
lot of
one of
space
those
in Canada.
ridge
I feel
tracks,
like
right?
Canada needs to get into this.
Actually, Phil told me this,
Yeah.
that